Hello all, we're going to be looking at an extension of those differential equations. So a really good way of being able to visualize something is to actually draw what we call a slope field. Now I have two ways that we're going to look at. We're going to look at drawing a slope field using GeoGebra, drawing a slope field using Desmos, and then also drawing a slope field with a good old pen and paper or just by hand. So I want to try this first one. I want to try this first one over here. Um, if we were trying to find all of these little, like their slopes at that line, what we could essentially do, this is like the point 1 right here. So if I plugged in my point 1, 0 for my x and my y over here, I would have 3 to the first times 1 plus 2 times my 0 and then minus 4. So I would actually have a y prime value of -1 right here. And you can actually see at this point, my slope value is exactly -1. And so that's what we've done with every single one of these values on here. It's kind of time consuming, but it gives us a really good picture because, for example, if I were trying to find the solution that actually went through this point, this would be the point 2, 1 right here. I would kind of follow along with what it is doing to the right and to the left of that. So it might be something like that for my solution that I would pass through that point, 2, 1. If I were passing through this point right here, so 0 and then 1, you could actually see that my slope is a little bit down and it's going to be following that. And then also kind of getting close to, it looks like we have an asymptote up here. We have an asymptote up here. So we're going to talk about like what those solutions actually mean, but I want to click on this GeoGebra slope field. And I'm actually going to plug in that equation that we just had right here, which was 3x plus 2y minus 4. And this gives us the same slope field that I had, but now I can actually look at that point 2, 1, and you can see, hey, that was about the solution that I had, and it's approaching an asymptote on this side. But if I switch it, all of a sudden, now my slope field is actually going off in this direction that I would have over here, or that particular equation would be going off in this direction according to my slope field. I want to do that with the Desmos slope field as well. So this one should be kind of familiar to us. The thing with this is it doesn't tell us a particular solution, but I can also move this around and that tells me what my slope is at any point. So at this point 0, 1, it looks like my slope is like that, so I can keep on following that slope and know that it's going to go down, 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 down this way. Okay, so GeoGebra is amazing. It was really helpful when we were doing like 3D rotations and things like that. It's going to be really helpful for these slope fields. So I know I could just plug this in, but I want us to get like a good idea of what is actually happening over here. And so normally we do like an X and a Y. We plug in our X, we plug in our Y to get our Y. But in this case, what I'm actually going to do is I'm going to plug in both an X and a Y value to find out what my slope, to find out what my y prime value is when I plug it into this equation. So I'm just going to pick this point 1 and then 2 as my y, and I can tell that my slope at that point is going to look like -1 over 2, or -1/2. Now -1 would be like this, and so I'm just going to go a little bit steeper than that at that point that I would have right there. Okay, let's try it for, I don't know, this point right here. So 1, 1. So if I'm plugging that into my equation y prime, I would end up getting -1 over 1. And so my slope is just going to be a -1. It's going to look something like that. And if I start filling this in for some more values, let's see what I get over here when I plug in 1, 0. So I'd have y prime is equal to -1 over 0. Uh-oh, does not exist, which means that it's actually going to be straight up and down. Our slope does not actually exist there. If I continue plugging this in, I'm going to get something to look like this. which actually looks like if I were to start at any one point right here, it'd kind of look like the solution of a circle that is centered around 0, 0. This actually does have the solution, -1/2 y squared plus 1/2 x squared equals c squared. So it does actually have the equation of a circle. We will talk in our next chapter how to actually find that. If I try to actually do that on here, some stuff ends up falling apart because it can't handle the does not exist slope that is straight up and down right here at the -1, 0, and at the 1, 0. But it will actually have a solution of a circle. So we want certain ways to be able to talk about the solutions that we have here. So anything that has a slope of 0, so all along my y-axis I have a slope of 0. Wherever that happens, we actually call that a type of solution. And we're going to characterize our solutions as equilibrium solutions. In this case, that is when my slope, when my y prime is actually equal to 0. So if I go ahead and solve this equation, it looks like that's going to happen at two values. It's going to happen at +2 and at -2. So I actually want to sketch that out here. And once again, I could just plug in a bunch of x and y values and then figure out what my y prime is equal to by plugging in those values for my x and well, it doesn't matter what my x is actually at all. It just matters what my y is because my y prime is going to be y squared minus 4. So it doesn't matter what my x is, but if this is 4, then my y prime is actually going to be 16 minus 4 is going to be super steep. So 12. So at 0, 4, this is going to be like almost up and down. And that's going to happen no matter what my x value is. So it's going to happen all along here. And if I keep on doing that for all of my x, all of my different y values, I will get a picture that looks like this. Picture that actually looks like this. So we're asked to look at the point 0, 3. So this 2, this y equals 2 right here, it is an equilibrium point, but we would call it unstable because this line is going away from it. This line is going away from it. If I were actually looking at this point down here and I'm looking at the equilibrium solution of y equals -2, you can see that points that are close to it are actually getting sucked in by -2. So they're getting closer and closer to that equilibrium solution. We would call this a stable solution. And we're going to look at something that is called a semi-stable solution. I just actually label what we had here. So a point that is getting sucked in to one of those equilibrium solutions on both sides is considered stable. Something that is getting pushed away on both sides is unstable. So if we have something that is getting sucked in from one side and pushed away on the other side, we would call that semi-stable. So on my next sheet, I actually have the definitions. You don't have to worry too much about them. We're just looking at like on this point, this is getting pushed away. If I'm below it, if I'm actually below it, then I'm getting sucked to that y equals 2. So we would call this semi-stable because it's unstable above and then stable below. So we call it semi-stable. Okay, we already talked about this in that example above, and I'm going to skip this example, even though we can already kind of see this one would be unstable here, and this at 2 would be, it's going away up here, but then below it's actually moving towards, so this would be semi-stable. And I want to look at what we're calling Euler's method on our next page here. So what we're going to do is we are going to pick a point. We're going to pick a point. So we're given a point right here. And then we're going to use that point to find our slope and then use that slope to extend it to another point that is whatever many steps away. So let's just say that we're 1 away. So for example, let's say I pick this point right here, and then I am going to draw a straight line. So my slope field will give me this slope to my next point. And then from here, I'll find the slope at that point, which will send me to here. I'll find the slope at that point, which will send me to here. And you can see that if I make those steps, so this was a change in x of 0.5, but if I make it smaller, like if my change in x, my step value is actually 0.25, you can see that I start to approach the solution faster. To actually visualize it, if you click on this link, it will show you kind of what I'm talking about. So if we make our H size a little bit smaller, my step size a little bit smaller, we'll actually be able to approach it faster. And that of course depends on where I'm starting. So if I picked a different value that I was starting at, let's choose -3, 1, and a step value of just 1 right here, you can see I'm kind of all over the place. But the second I get a little bit smaller, I'll actually start to approach that solution. Now, it's only a good estimate near that point. The further you go away from that point, the more any craziness could happen. So we're going to find this table by hand, but this is a really, really helpful way for you to be able to see this. And also, the cool thing is you can turn on your slope field this way as well and see what's going to happen depending on what point you pick. Okay, so for this example up here, we are given, for Euler's method, we are given y prime is equal to 2x minus 3, and we're given this as our initial value. And then we're also asked to go, our step value is going to be h is equal to 0.5. So I'm going to go by 0.5. So I'll start out with 0, and I know that that was my point that was given to me, was 0, 3. And then now that I go to my next point, what I'm going to do is I'm going to take where I started, my y naught, which was 3, and I'm going to go 0.5 away. So you can see 0.5 is kind of like my slope. I'm going 0.5 away of whatever my f equals when I actually find that. So I'm going 0.5 away, and then when I plug this in, that is actually going to be my y prime. So that is actually my slope. And then this is how far of a distance I'm traveling with that specific slope. So if I plug 0, 3 into this equation, I end up getting that y prime is equal to just a -3. So like 2 times 0 minus 3. So that is my slope at that point. I'm multiplying that by 0.5, adding it to 3, and this will be my next point value that I have at the point that I'm given. So I've actually input these in, and so now that I'm chilling at this next point, so I went 0.5 away to get to here. Now that I'm chilling here, I'm going to find my slope at that point, and that'll lead me to this point right here. So in other words, this gave me the 0.5, and then my y value is 1.5. So now I'm going to go another 0.5 because that's what my h is here. And I'm actually going to find this by taking my value from up above, which in this case was my 1.5. That's what I found. Plus, I'm going another h, so I'm going another 0.5 of whatever I get when I plug in this point to my h, or my y prime up here. So this y prime value that I have, I'm going to be plugging in 0.5 for my x, and then minus 3, I guess my y value doesn't really matter a whole lot there. If I actually simplify this down, I will get a 1.5 and then plus a -1 when I do all of this math on the inside. So I'll actually just get a 0.5. So my x value was 1, and now my y value is 0.5. I'm going to do this one more time, and then I'll have you guys work on this. So to find this next one, I'm going to take my y value from over here. That's where I'm starting. And then I am going an h of a distance. So this h is also happens to be 0.5. And then I'll plug this whole point into my y prime. So I'll have 2 times 1 and then minus 3 right there. And so if I follow this through, I'll do 2 minus 3, which is negative 1, times my 0.5. So I'll have a negative 0.5 right there. Will actually give me 0. So 1.5 and then 0 is my next value. Go ahead and try that with these last few. Okay, so these are what I found for my points over here. And if we actually compare that to our Euler's method right here, we will see that those values are true and correct. And that's what we got. So like the 6 is that 3 and then the 1.5. Okay, on this next little problem, we're not going to do the whole thing, but I just want to like set it up. So let's say we're trying to do this with 5 steps. So what I'm going to do over this interval, so I'm going to see this is spanning 2, and I want to cut that into 5. And so what this is actually going to be is going by a step value of 2/5 or 0.4. So that's essentially what I just did over here because of this that I would have. So I'm going to start out at 0 and then go by 0.4 for my x value that I'm plugging in each time. And then I should end up back at 2 right here. So let's just do the first one together, and then we can kind of look at these points over here. So what I am starting out with is I'm starting out with the point 0, 1. So my y sub 1 right here, my first point is going to be the y value before it, which was 1 coming from here, plus my h value, which was 0.4. And then I'm going to multiply that by whatever I get when I plug 0, 1 into this function that I have up here. So I have 1 plus 0.4, and then all of that is going to be times 3x, which is 0, and then minus 1, which is my y. And if I follow this through, I will actually get 0.6. So my xy value looks like 0.4 and then 0.6. That'll be my xy value. If I just keep on doing this, you can check your answers. I'll get a y value of 0.84 here. I'll get a y value of 1.464, 2.3184, and then 3.311, with these corresponding to be my x values. Okay, y'all, that is Euler's method, and I hope you have a beautiful day. Bye.